So now I'm gonna watch these videos. It's getting late here, but I think I'll wait a little bit to turn on the light.
Determine how connected the two profiles are by various parameters. And this helps, for example, recommending the jobs, connections, political agendas, all these sort of things. For example, think about a political party where people within the party are having dispute among themselves, and if the party splits into two different groups, probably you want to be able to identify which members would join which party, and then social network analysis is a very good tool to get an understanding on such a thing. For example, another application is where you want to minimize the spreading of rumors. Then it's also important to have an understanding of the social network that you're dealing with. So in this tutorial, we're going to learn a bit about a tool that can help you on doing the network analysis, which is called NetworkX. And what I'm going to show you at the beginning is a bit of basic concepts about node and edge attributes and bipartite graphs. And then after that, you're going to have a look at a bit of more complex data set and do a bit of network analysis, not necessarily the data visualization, but for understanding the concepts and the network and the connections in the network. And at the end, I'm going to show you a few cool network visualization taken from the NetworkX own repository, just to show you that it is a versatile visualization tool as well. But we're not really focusing on that visualization aspect of the NetworkX in this video. But if you are interested, you can have a look on the NetworkX manuals and tutorials. I will put a link in the description box to that as well. You can also get the link to this code and any dataset that is used here in the description box. So let's start. What we need to do first is basically to import the packages that we need. And for today, basically the most important thing that I need is the NetworkX that I'm importing it as NX. And you need to, you could have some attributes. In this case, we're thinking about the weights that determines the strength of relationship between two nodes. And just to have a bit of more flavor, we're also going to add some different relationships. For example, if two people, we're thinking about people in this context, are family members, are friends, or they are enemies. So what I'm going to do here is first build an empty graph with the network X, and then I'm going to add edges basically. And at the same time, when you're adding edges, you're adding nodes as well. So basically what I'm saying in the first line is that I want to add an edge between two people called A and B, and the relationship, the strength of the relationship, think about it, is like 13, and in this example, it's probably one of the strongest one, and they are friends. Similar to that, B is also a family member of C, and the weight is 9. B is also a friend of D. The weight is 7, which is a bit lower than the previous ones. And E and B also are friends. E and A doesn't have that much of a good relationship with each other, and B and F are family members. And this is what I'm going to have here, and I'm going to build my graph. And this is basically give you an overview of the edge. It's basically what you put there, the weight, the relationship, and the nodes. You could also assign some roles to the nodes. What I'm doing here, for example, I'm saying it's only connected to B. So as you see, even so, it's all really B with E, F, D, and C. And as you see, A is also connected to B, but also to E. Everybody else is also connected, is only connected to B. So as you see, even within this simple network, you can immediately get a feeling of the connections. Nobody is connected to each other except B that is holding network together, and A that has another relationship with E. And if you look at the labels, this is not actually a very close relationship. They are enemies. So it gives you an indication just by E is group 1 and 1 to 4 are group 2. And basically what I'm going, as you see, that let's get folder and then you can have a look, and then we are going to have a
I have a sense that this video doesn't have what I wanna know. She's not gonna talk about it. About the things that I'm interested in understanding.
to say if the person's historical significance, you're going to put them in a list, then index 0 is when you start counting in Python, and so the person's historical significance will be index 1, then gender will be index 2, and so on. So we build our dictionaries like this, as you see, historical significance node 1, 2, 3, 4, 5, and so on. And now you have a set of dictionaries that you can use to add attributes to nodes in your graph object, and the set node attributes function takes 3 different variables: the graph to which you're adding attribute, the dictionary of ID attribute pairs, and the name of the new attribute. And the coding for this. You can find it here. Basically, I'm just writing them more clearly in a sense. Now we have all these 6 attributes, and we could access them anytime we want. For example, if it's basically getting the ratio of what exists and over what could exist. In an undirected network like this one, there could be a single edge between every 2 nodes, but only a few possible edges could be present at the moment. And network density gives you a quick sense of how close-knit your network is. And the good news is that it's quite actually easily done in Python, but with one single line comment. And this is as simple as, where is it? Yes, density and x density for the graph G. And this is what we are getting here. The output of density is a number, so that when you'll see the value when you print your value, and in this case, the network is the density of network is approximately 0.002, and on the scale of 0 to 1, this is not actually a very dense network, which is what you could also see when we are doing the network visualization. I can actually try to do that. Let me copy that so I don't need to print it again, type it again. Probably it was easier if I had.
I think I'm just gonna read the class there to understand what's going on.
And basically, this measure is essentially finding friends of my friends of friends. If my mother knows someone and I don't know, the mom is the shortest path between me and that friend. And to calculate the shortest path, you need.
Maybe it's not possible to create a narrow representation of the nodes using this network.
We are at the mercy of those tools like Gephi on what we can do and what we cannot do. Here's the good news. NetworkX gives us immense power on what we can accomplish using our graphs on networks. In this video, I'll talk about 3 things. First, I'll show you the very basics of NetworkX, how to create a graph, how to add nodes and edges to that graph, how to add attributes to those nodes and edges, things like this. In the second part, I'll show you how to visualize that network. And in the third part, I'll show you how to implement some of the most widely used network models like Arder-Shreni random graph models and Barabasi-Albert preferential attachment network models. One thing I'll not talk about in this video is graph algorithms. I'll leave it for another video. So let's go to my computer screen and get started with the very basics of NetworkX. Before we get started with coding, I think it would be useful to take a look at the documentation of NetworkX. For that, you can go to your browser and type networkx.org/documentation, or you can simply Google for NetworkX documentation. It'll take you to this website where you see how to install NetworkX. For most of you, this one single line of command, pip install NetworkX, this will do the installation. However, I would recommend you to use Anaconda's Python distribution because it comes pre-packaged with NetworkX and many other Python packages. So if you are using Anaconda, you don't need to install NetworkX separately. On this website, you also see there's a tutorial section. It's actually a pretty good tutorial, and in this video, I have borrowed a lot from this tutorial. There's also a reference section here. If you're doing any project using NetworkX, you'll be looking up this reference a lot. Here, if you scroll down, you'll see there's an algorithm section, a wide variety of course, you can change it anytime by clicking diagram. Okay. We'll then add a few nodes to our graph object G. There are 2 basic ways of doing it. One is we can say g.add_node 0. Here, 0 is the node object that we want to add to our graph. Of course, 0 is a number, but in general, the node object doesn't need to be a number. It can be a string, it can be a tuple, it can be any hashable Python object. Okay. Huge number of nodes that we want to add to our graph. For example, if you have 50,000 nodes, there's no way you are going to write 1, 2, 3, up until 50,000. And a better way of doing it would be by using range. Okay. Next, I'll talk about how to add edges to our graph. Again, there are 2 basic ways of adding edges to a graph. One is we can say g.addEdge. In this case, we are saying 0, 1. This will add an undirected edge between nodes 0 and 1.
We can add the whole list of the data frame all at once instead of doing the loop.
There's a second way of adding edges. We can say g.addEdges from. Then we are giving it a list of edges that we want to add, and each edge in this list is represented as a tuple. So for example, the first tuple is 1, 2. This will add an edge between nodes 1 and 2, an undirected edge, of course. Then the second tuple is 2, 3. The third one is 3, 1. So in effect, we are basically adding a triangle between 1, 2, and 3 to our graph. And this triangle would be added on top of the previously added edge between 0 and 1. Okay. Next, if you want to access the number of nodes in our graph, you'll say g.number of nodes. And similarly, there's a g.number of edges for getting the number of edges in our graph. Okay. And after that, I'll talk about 4 views that NetworkX provides us. Views are basically objects defined on top of dictionaries. We know that a dictionary can be modified dynamically. So these views reflect this dynamic modification of a dictionary. And by the way, dictionaries happen to be the bread and butter of the behind-the-scene data structures in NetworkX. The first view is g.nodes. At a very high level, you can think of this view as a collection of nodes that we have in our graph. In particular, we have this node 0, 1, 2, 3, these 4 nodes. So g.nodes represents this collection of 4 nodes. Similarly, g.edges is the collection of 4 edges that we have in our graph. G.degree, this view gives you the degree of each node in our graph. Okay, and the last view is g.adj. This gives us the adjacency data structure in our graph. This one is a little bit complicated compared to the other one. So what I'll do now is I'll run this program. This visualization is the effect of some code segment that I have later on. I'll get to that in the second part of this video. So first of all, we see the number of nodes equals 4. This is basically the output coming from this print statement. The second one is number of edges equals 4. Again, this is coming from the next line of code. And then we see the 4 views. G.nodes, the node view is 0, 1, 2, 3. It's basically a list of nodes that we have in our graph. And the second view is G.edges. Okay, so here you can see that it is represented as a list of tuples. Okay, each tuple represents an edge, like 0, 1 is an edge, 1, 2 is the second edge, 1, 3, 2, 3. So these are the edges, and you can relate to it by looking at this visualization. The next view is G.degree. Here it's a list of tuples once again. So the first element in each tuple, 0, in this case, 0 represents the node object, and the second element in each tuple represents the degree of that node. Okay, so it's saying 0 has a degree of 1, 1 has a degree of 3, node 2 has a degree of 2, and so on. Okay, again, you can relate to it by looking at this visualization. Okay, and the last view is G.adj. As I've mentioned, this is a little bit complicated. It's a dictionary of dictionaries of dictionaries. Oh boy. So there are 3 levels of dictionaries. At the first level, we have the keys are basically the nodes. For example, 0 is a node. So 0 is a key at the first level dictionary. And at the second level dictionary, we have the neighbors of 0. And in our case, we only have one neighbor for 0, that is node 1. So that's the key in the second level dictionary. And this neighbor is mapping to a third level dictionary, which is currently empty. It's going to represent the attributes of this relationship between 0 and 1. So we have an edge between 0 and 1, but we haven't added any attribute to this edge. As a result, this dictionary is empty. Later on, when we add some attributes to this edge 0, 1, we'll see that the attribute.
So maybe this is getting that this dictionary. And then it's getting the idea here of each node. Which is going to be that attribute that he's talking about.
Attribute name and value. This name value would be represented as a dictionary right here. So this is basically the representation of the adjacency structure in our graph as a dictionary of dictionaries of dictionaries. If it seems complicated, I would just mention that you can live a very happy and fulfilling life without ever having to use G.adj. I'll show you how. Okay, so let me clear out this output. I'll next talk about how to add attributes to our nodes and edges. There are 2 attributes that I want to add to each node. One of these attributes is the node's smoking status. True means smoker, false means not a smoker. Okay, and the second attribute I want to add is the node's body weight. And I want to add this smoking status arbitrarily and the body weights randomly. This is how we can do it. So here I have a loop for I in G.nodes. So basically this loop is going through the nodes in our graph, and obviously G.nodes is the view that I just showed you. And by the way, this is the number 1 most widely used graph operation, going through the nodes of the graph. Okay, so for each node we are saying G.nodes bracket I. Okay, then bracket smoking. So this is new. This is smoking in quotation. This is a string. This is basically the node's smoking status or smoking attribute, and I'm setting it to false. Initially, all of the nodes are non-smokers. Then for the second attribute, I'm writing G.nodes I weight, and once again, weight is basically the weight attribute of each node, and I'm setting it to a random number between 100 and 200. Okay. Next, once the loop is finished, I'm arbitrarily setting node 1's smoking status to be true. Node 1 became a smoker now. Okay, next I'll talk about how to add attributes to the edges in our graph. For that, I've written a loop for E in G.edges. Once again, this loop going through all of the edges in our graph is a widely used operation. So for each edge E, we are saying G.edges E, and the strength, this one is the edge attribute. We are saying equals round. We are rounding up a random number to 2 digits after the decimal point. Okay. So first, I'm going to uncomment this line of code and run it and show you the node data. So again, you'll see the coat hanger graph appearing here, the visualization. G.nodes.data. It represents all the data about each of the nodes that we have in our graph. So it is represented as a list of tuples. Okay. So the first item in the tuple identifies the node. In this case, for example, here you have node 0, and it's saying the smoking status of node 0 is false, and the weight is 174. This 174 is a randomly picked number between 100 and 200. So the first element of each tuple is the node object, and the second element of each tuple is a dictionary of attribute names and attribute values. Okay. Next, I'm going to comment this node data, and I'm going to uncomment the edges data. And I'm going to run this code, and the same coat hanger graph appears here. So it's basically saying the strength of this edge between 0 and 1 is 0.25, which is a randomly picked number. The strength between 1 and 2 is 0.07, and so on. Okay. Next, I'm going to show you the output of g.adj. So it's the dictionary of dictionaries of dictionaries. I said that we don't really need to use it, but it's good to understand what g.adj does. So I just uncommented this line, and I'm going to run this program again. And you'll see that g.adj represents the same information as g.edges.data in a different format. So this is the g.adj dictionary of dictionaries of dictionaries. At the first level of dictionary, you have the node 0. At the second level of dictionary, you have the neighbors of node 0. In this case, we have just one neighbor, that is node 1. And at the third level of dictionary, it identifies the relationship attributes between 0 and 1. In this case, it's a dictionary where the key is the attribute name, strength, and the value is 0.68. Okay, you can see that the value changed from the previous run because we are randomly picking this strength. Okay, and you can relate to the other items in this dictionary of dictionaries by comparing it with g.edges.data. Okay, so once again, let me clear out the output. One of the powers of NetworkX, and sometimes one of the confusing aspects of NetworkX, is that there are multiple ways of doing exactly the same thing. And this is what I'm going to show you. I'll show you 3 ways of iterating through the neighbors of a node. For that, I'm uncommenting this code segment. So the first way, and by the way, this is the number 2 most widely used operation in graphs, that is iterating through the neighbors of a node. Okay, and I'm just picking node 2 arbitrarily here, and I'm going to iterate through all of the neighbors of node 2. The first way is we can use a loop that says for NBR in g.adj bracket 2. So here we are using the adj adjacency view, and we are printing the neighbor here. The second way, which is actually equivalent to the first way, is we can say for NBR in g bracket 2. You can see that we have just omitted .adj here. Instead, we just said g bracket 2. And in fact, it is defined exactly the same way as g.adj. It's also a graph view, and it's going to give you the same output as the previous loop. And the third way is we can say for NBR in g.neighbors parenthesis 2. So make note of parenthesis 2 versus bracket 2 in the previous 2 code segments. Okay, so we are iterating through the neighbors of g, and we are printing the neighbor. Okay, you can see that all 3 loops gave us the same output, 1 3 1 3 1 3. So if you ask me this question, which one should I use? Should I use g.adj or simply g or g.neighbors? To answer that question, there's one really important thing about coding called readability of code. In that regard, if somebody sees this code segment for NBR in g.neighbors parenthesis 2, as soon as they look at this g.neighbors in parenthesis 2, they know that you are iterating through the neighbors of node 2. And for that reason, I would say that writing the third way, going with the third way, is basically the right way to do things. Okay. In this segment, I'll talk about how to visualize our graph. To visualize our graph, first of all, we'll create a figure by saying plt.figure in parenthesis 1. That is, we are giving the figure a number 1. And there's a simple one line of code that we can use to visualize our graph. We can just say nx.draw_networkx in parenthesis. We are giving the graph object g. However, we'd like to do something a little bit more elaborate. We'd like to color each node by their smoking status, red for smoker, green for non-smoker. We'd also like to resize the node according to their body weight. To do things like this, we'll create a color map list. We'll also create a size map list. Okay, and then we'll go through each node in our graph, and we'll be appending to size map the node's body weight times 2. So this times 2 is kind of arbitrary. It's just to magnify the number. And then we are saying if the node is a smoker, then we are adding to color map this is string red. And otherwise, we are adding to the color map this is string green. Okay, I'll just briefly mention that NetworkX recognizes these color strings, the basic colors like red, green, blue, all of these basic colors. And then we are going to create a layout, graph layout, by saying nx.draw_networkx. We are supplying it the graph object g. We are saying the node color is this color map. Node size is represented by the size map. And then we are saying position, that is pos equals nx.string layout, which is a graph layout where if 2 nodes are connected by an edge, they attract each other. And if 2 nodes are not connected by an edge, they repel each other. So these forces of attractions and repulsions here will play out for 1000 iterations. And finally, we'll get a graph layout. And then we are saying the arrows equals false means that we don't want to show any edge arrows. And with labels equals true means we are going to show the node labels. Okay, so this function nx.drawNetworkX, it'll create a graph layout, but it's not going to show the graph immediately on your screen. To show the graph on our screen, we'll have to say plt.show. That is, this line of code will show the figure 1 on our screen. Okay, so let me run this code again. You'll see that this visualization that we have been seeing all along, this is coming from this code segment. Okay, and another thing you probably noticed is that the code hanger, the location of the positioning of the code hanger was changing all the time. Is because this spring layout algorithm starts with a random initial position of all of these nodes, then the forces of attractions and repulsions play out, and finally we get a visualization. Okay. First, I'm going to talk about how to create an Ardo-Shenanian random graph and how to plot the degree distribution for that random graph. To do that, we are creating our second figure here. Then we are creating a graph object g underscore ardosh by saying it's equal to nx.ardosh underscore reni underscore graph. So this is basically NetworkX's Ardo-Shenanian random graph generator. It takes two parameters. The first parameter is how many nodes we want. In this case, let's say we want 1000 nodes. The second parameter is with what probability are we going to connect any two nodes. Here we are going to connect any two nodes with a probability of 0.1. Okay. Then we are creating a list of the degrees in our graph by saying degrees equals, this is a list comprehension that says g underscore ardosh dot degree. That is, we are using the degree view of our graph object, bracket I, that says the degree of node I for I in all of the nodes in our graph. So this will be a list of degrees of all the nodes in our graph. Okay. Then we are putting the x-axis label to be k, which is the typical notation for the degree, and y-axis label of p underscore k, again typical notation for the proportion of nodes that have the degree k. In this case, we are interpreting it as a frequency of nodes that have degree k. Then we are setting the title of that plot, and this is the histogram plot that plots the degrees, and these are the bins in that histogram that go from the minimum degree to the maximum degree. Okay, we can do a similar plot for Barabasi-Albert preferential attachment network, and to do that, we are creating our third figure. We then say g underscore Barabasi, this is our graph object, equals nx dot Barabasi underscore Albert underscore graph. This is NetworkX's preferential attachment network generator. It also takes two parameters. The first parameter is how many nodes we want. In this case, we want 1000 nodes. And remember that in Barabasi-Albert preferential attachment networks, nodes are born one at a time. So this is a growing network model. Upon birth, a node forms a certain number of links with pre-existing nodes. The second parameter tells you with how many pre-existing nodes a newly born node forms links. Also relevant here, these links are formed proportional to the pre-existing nodes' degrees. In other words, these two figures. Trust between these two.
A good video, but I still have many questions. So I think I'm gonna read this stuff to understand how it is creating the graph. Given a mandatory node ID. No labels default to node IDs if no label is specified during the call. Node ID. So maybe it should be passing node IDs. I can create a variable and then assign it to the first one and assign the variable plus one to the other one. The ID of the node, the ID is mandatory for nodes and they have to be unique. This should obviously be set per node, not globally. Label is the piece of the text shown in or under the node, depending on the shape. Hmm. So here I can do underscore RD. And create a variable here. So this should allow me to figure out the index of each one. Use it on the data frame later with the data frame. So for some reason this is giving me a mistake here. So should probably, oops. It's probably the indentation here. Yeah, there we go. Unexpected spaces. I'll be right back. I think I'm gonna print this neighbor map thing. So it's interesting that I didn't put label. I guess the title works as a label. Not an undefined, the node will belong to the defined group. styling information of that group will apply to this node. Node specific styling overrides group styling. Hidden when true, the node will not be shown. It will still be part of the physics simulation though. So image, label highlight bold. Determines whether or not the label becomes bold when the node is selected. So assume is a Boolean value that accepts. So maybe I should use this one. So I think we're gonna run this just to see what happens. Level, when using the hierarchical layout, the level determines where the node is going to be positioned. Parameter mass. The Barnes-Hut physics model, which is enabled by default, is based on an inverted gravity model. By increasing the mass of a node, you increase its repulsion. Values lower than 1 are not recommended. Oh, that's also interesting. Using the hierarchical layout, the level determines where the node is going to be positioned. Now I didn't create anything in the graph. So obviously that should be one of the things that I added here. I'm gonna erase this, see if it works. Hopefully it does, because this ID would be really useful. Also, I'm getting a bunch of exceptions here. Or maybe not. Maybe just the neighbor map stuff. Got multiple values for argument and ID. Oh, so I guess. Oh, that's the problem. I guess when it gets the same values, it creates the same node, so I can't use the NID. So it's not building the graph the way that I was thinking that it is building. Maybe if I try to put it, so let me see the other way. If I leave this highlight thing here, maybe I try to put in the edge instead. Yeah, but the edge doesn't have an ID. So I just have to think about something else. The shape defines what the node looks like. There are two types of nodes. One type has the label inside of it, and the other type has a label underneath it. The types, oh, now it looks like it created a graph. One, the types with the label inside of it are ellipse, circle, database, box, text. So these are the ones that I want. The label inside. Circle, database, box. The ones with the label outside of it are image, circular, image, diamond, dot, star, triangle, triangle, down, square, and icon. The size is used to determine the size of node shapes that do not have the label inside of them. These shapes are image, already read that. Title to be displayed when the user hovers over the node. Oh, so the title is different than the label. The title can be an HTML element or a string containing plain text or HTML. So I think we will use this shape circle here and see if it's good or not, if I like it or not. Oh, I forgot to. Damn. Let me open this again. Forgot to see if it's highlighting when I pass through. So it's getting the div here. Nodes equals new vis.dataset. Parsing and collecting nodes and edges from the Python. Hmm. Oh, so it automatically puts the label the same. Oh, it's making the ID equals me. Hmm. Oh, I understand. The first argument is the ID. That's why it wasn't working there. Annoying little thing showing up here. Adding nodes and edges to the graph. Data equals nodes. Nodes, edges, edges. False, edges, column. Hmm. Yeah, just by looking there, I don't understand really well. Yeah, so it is highlighting. Nice. I think I'll also change the color eventually. I didn't see if it printed. Yeah, you printed a bunch of stuff, so I guess it's this neighbor map thing that is printing. And apparently, it is that dictionary that the guy talked about. Maybe I should just print the first one. So main then has the dictionary. Main equals this. This equals main. Yeah, so this contains the adjacent nodes. Also want to understand what this node is here. I guess it's each node that I created here. Every time you create, it gets you add a node to the network, it gets added to the list that is the network attribute. So assume that dot nodes is the list, yeah, is the attribute with the list of nodes, and each node is gonna be. So here is adding the title attribute of the node to this thing here. which I assume is getting the connections. So it's adding this text to the title here. Add neighbor data to the node hover data. I think I'm gonna close this for now.
Hello again and welcome back. In this
We should increase the strength of this light. Not really sure. Then it's changing the value to the length of the dictionary. So that's why it's increasing the size of the ball there. Because it's making the value equal to how many connections each one has. Hmm. So I guess I can make the color based on this attribute as well. I can make it if this value is equal or bigger than some number, then I change the attribute of the node, the color, choose some different color. And I guess that will show me which connections are more fundamental. But then that would still not give me a good idea of what parts are usually used when building scripts. Yeah, but I think it's good enough. But now the problem is trying to understand, trying to see if there's a way that I can build the arrow to show the path.
video, we're going to pick up right where we left off in the last video. And instead
Oh,
of
I
plotting
forgot to
simply
change the
nodes,
shape there. That's what I was gonna do. So I think it should be like this. When a value is set, the node will be scaled using the options in the scaling object defined above. X. This gives a node an initial X position. When using the hierarchical layout, either the X or Y position is set by the layout engine, depending on the type of view. The other value remains untouched. This gives a Y position. String or int, number. Assert is instance or is instance. If label, no label. Else node label equals then ID. So I guess I can use the label. I can use the label to get the sequence, the order, make the label equals to the thing. Equals to I. But it is a string though, so I guess. Let's see. String or int. Okay, so accepts int. So label. Okay. So I think I'm gonna put it there. Actually, I think I am. I wasn't sure if I was gonna create a variable just to show the first iteration, but I think I'm gonna do this. Just so it's easier to see there. So here, since it didn't, I'm gonna put label equals I plus 1. And here I'm gonna do I equals 0. Now it should work, I guess. Oh, that was fast, but it doesn't look like it's working. Got multiple values per argument label. Hmm. And that's the problem. Not sure if there's a way to get the order. I can just use the index of the list. Yeah. So I can use the index, and the index is naturally gonna contain the information because these net nodes here probably is the list of the nodes. So I guess the index of them, if I loop through the list, I can create the thing that I want. And maybe I can use this on the other scripts as well. But I'll have to think about. Yeah, I have to think. So if NID not in self.node that is n equals node NID shape label self nodes dot append and options self nodes node IDs dot append. Well, let me see. What do I get here? So node is this thing here. So it's dictionary for properties of each node, I guess. Title, main, neighbors. Huh. So it didn't have this before. Node ID is just main. I guess I'm gonna put this before. No. So next time I run it, I can see how it looks like. I imagine it's just gonna be main here, and then it's not gonna have this. Maybe I can print this neighbor map as well. Yeah, neighbor map already. I'm also gonna print. Oh, I don't think I'm gonna print neighbor map. Def add nodes. So this one is add nodes, just for one node. Add nodes. This method adds multiple nodes to the network from a list. Default behavior uses values of nodes for node ID and node label properties. You can also specify other lists of properties should go along each node. So it might be easier to just create a NumPy array out of the series. Out of the column of the data frame and just use add nodes instead of doing the whole looping thing. The only issue is gonna be these properties. Size, title. Type nodes list. So size, value, title, XY label, color, shape. For key and QRX, assert key. Leaf nodes. For node in nodes. Check if node is a number like now add edges. Damn, this is taking a long time. So with circles it actually takes longer. I'll be right back. Then I'm curious to see if it works, if it worked or not. Based off the IDs of the nodes. Order does not matter unless dealing with a directed graph. Ah, so that's the thing. Order does not matter. Self-source true options. I'm having a hard time understanding what an edge is. I guess is the connection. That's how I look at it now, but it's done based off the IDs. Add edge 0 on as an edge from node ID 0 to node ID. 0 on value equals 4 adds an edge with a width of 4. And false, the edge stops at the arrow. This can be useful if you have thick lines and you want the arrow to end in a point. Middle arrows are not affected by this. Parameter from. Edges are between two nodes. One to and one from. This is where you define the from node. You have to supply the corresponding node ID. This naturally only applies to individual edges. Yeah, so I guess it's like it says. It's the connection. But it doesn't say that if there is a way to. So this is obviously way worse than the other graph. Yeah, the other one's gonna be way better. And here the edges don't show as well. I guess they're on the background. I think I'm gonna try a couple of different shapes just to see what it looks like. I think I'm gonna try all the shapes actually. So we have circle, ellipse. I think is gonna be pretty similar, but this database I'm not sure. How it will look like. Yeah, and I think there is not going to be possible to, at least using this NetworkX, to demonstrate the direction of the thing. Yeah, but it's probably going to be possible to make it so I can click on the thing and figure out which file it is. Or yeah, the issue is if a node is not a file and it's a function, then I have to see the connection and not the node itself to get the file. So let me run this. I guess I can take this off again. arrow strike through. Oh, so there is an arrow currently. When false edge stops at the arrow. This can be useful if you have thick lines and you want the arrow to end in a point. Middle arrows are not affected by this. So is this where I stopped before? I guess so. It's not matter when dealing direct graphs. So I guess I skipped this. Or am I insane? I think I skipped this one. Yeah, I went directly to add edges, maybe. Maybe not. I'll keep reading. Adding edges is done based off the IDs of the nodes. Order does not matter unless dealing with directed graphs. So I also have to see directed graph. Maybe it's better. Anti add edge. Arrow strike through. When false, the edge stops at the arrow. This can be useful if you have thick lines and you want the arrow to end in a point. Middle arrows are not affected by this. Edges are between two nodes, one to and one from. This is where you define the from node. Now to supply the corresponding node ID. This naturally only applies to individual nodes. And true, the edge is not drawn. It is still part of the physics simulation, however. When true, the edge is part of the physics simulation. When false, it will not act as a spring. That is shown in the pop-up when the mouse moves over the edge. Parameters 2. Edges are between two nodes, one to and one from. This is where you define the two nodes. You have to supply the corresponding node ID. This naturally only applies to individual nodes, to individual edges. The value set, the edges width will be scaled using the options in the scaling object defined above. The width of the edge, if value set, is not used. So I'm gonna put this to true, obviously, next, to see what it does. Verify nodes exists. Assert source in self.get nodes. Non-existent node, string source. Assert true in self nodes. We only check existing edge for undirected graphs. So I guess one thing that I can look at is difference between direct and direct NetworkX graphs.
Hello friends, now we are going to see the types of graphs. So see, first type is undirected graph and the second is directed graph. In my first video in this series, I have introduced these types. So let's see in detail. So this is the undirected graph. As you know, in undirected graph, if we specify that there is an edge between x to y, then it also means that there is an edge between y to x. Okay, that means if you say there is an edge between a to b, then that means that there is also an edge from b to a. So this relationship is like the friends relationship on Facebook. So on FB, If you are a friend, means if A is a friend of B,
So I have to build a directed graph apparently. I think I need to specify this when creating the object itself. The other thing I was thinking about it when I was working out today is that it's not only the functions, there's also scope of execution. It's not only the lines of code. So I think that's the problem when if I try to use the graphs to build scripts, to try to reverse engineer the process somehow, is that I'm probably going to be losing information. Yeah, but it shouldn't be that important because it's the flow of the thing that matters. And the other thing that I thought about is that if you it's probably required to have multiprocessing on more advanced scripts, because if the graphs are kind of like connections between neurons, then the execution scope is going to be like the flow of the chemical signals between neurons, which means that you need to have more neurons firing at the same time simultaneously, probably to solve more difficult problems, which means that you need more threads, because in my mind at least, the way that you would be represented is the execution line by line. It would be like the neuron firing off. So the electricity passing through the connections, and the multi-thread uh, scripts would be like several neurons firing off at the same time. So this function writes the HTML, gets the data structures, supporting the nodes, edges, and options, and updates the template to write the HTML holding the visualization. So this is the one that I'm interested about as well. Check HTML name. Here check if an href is present in the hover data. Use link template equals false. For n in self.nodes, title equals n.getTitle, none. If title, if href in title. This tells the template to override the default hover mechanics, as the tooltip would move with the mouse cursor, which made interacting with hover data useless. Use link template true. If not, notebook with open soft as HTML content equals HTML.read template. Else template equals the south template. I don't understand how this becomes HTML. Self.html template.render. So I guess that's how you build an HTML page using this template. No, here it is with open name as out.write self.html. So I guess this is the function used to write HTML. If notebook return iframe name with self.with find self.type. Writes a static HTML file and saves it. Saves it locally before opening. The name of the HTML file. So it's really not that complicated. It's not as complicated as I thought it would be. I just didn't know that you can use this function here to write an HTML file. Load the template data into the template attribute of the network. This should be done in Egyptian notebook environment before showing the network. Set template from dots. This method takes the contents of dot file and converts it to a PyVis visualization. Assuming the contents of test.dot contains the graph sample tree. Usage of the dot file being converted, type dot equals dot file. And this is the dictionary stuff. This method returns the user and the adjacency list representation of the network. Also, I think this might be slightly different than the thing that the guy was talking about in the video. Returns dictionary mapping of node ID to list of node IDs. Or maybe not, maybe it's the same thing. Dictionary mapping of node ID to list of node IDs it is connected to. In self.nodes, a list IID equals sat. In self.directed, for e in self.edges, source equals e from, destinations equals c true. Else source def neighbors. Given a node ID, return the set of neighbors of this particular node. So I guess the reason why the graph is displayed that way is because the leaves of the trees are the functions, I guess, and the bigger nodes are the files. That's why it's being displayed that way. And if that's the case, then I can probably figure out, probably write something with the number of connections. If it is bigger than a certain amount, I get the neighbors. Maybe that's not necessary because getting the file is more important than getting the functions, I guess. Oh, the other thing that I want to try to do, instead of doing like this, where I'm connecting function name with function file name, connecting function file name with caller file name. I think I'm gonna try that next. I think that makes more sense actually. Although both of them are useful, obviously. Parameter node. The node should get neighbors from node string or these instance nodes are expected int or string. Insert node in soft.nodes ID. Node not in network. From and sys and x and shit. This method takes an existing NetworkX graph and translates it to a PyVis graph format that can be accepted by the Vis.js API in the Jinja 2 template. This operation is done in place. It turns an iterable list of node IDs. Turns list. And so I can use this get node. The thing I'm not sure about is that I don't think this information gets stored anywhere. So I'll probably have to create the... But the thing is, I already have the data frame anyways. Yeah, but if I wanna play around with the graph and connect the graph with the data frame, it's gonna have to be stored. It's gonna have to be stored in a different format other than the data frame. Yeah, this one is obviously not good. So let me see what else. What other shapes? Circle, data box stacks. I think it's gonna have to be outside of it. That's the diamond. Yeah, so in each pass directed equals true. True if using Jupyter Notebook. So I'm gonna test this directed equals true. Next. Then right after that, I'm gonna change the source. Just see how different it's gonna be. Make the source equals caller file name. And the target, the function file name. No, the other way around. Source equals function file name. Target equals caller file name. Or maybe it makes more sense to have the caller as the source. But I'm not really sure if it makes a difference. The thing that I'm trying to think about is how I'm gonna make it so that the graph is connected with the data frame. That seems to be the hardest part. I need to create a script that... Oh, I can actually... Yeah, the thing is, that's a problem. I don't know if it gets... It probably doesn't get started. After I run this script and create a graph, there's no way to access the network object, I think, anymore. And that's what I'm having trouble with understanding. Because that means I'll probably have to do... I probably... This information is not going to be useful. Because I'll have to play around with the HTML file. And I won't be able to access this object. So I'll probably have to think about a way yeah, I'm gonna research how to make Python scripts. Well, maybe I actually think I know how to do that. I can just use get element by ID and then activate a Python script. Then I can just change the function there on the JavaScript of the HTML file and make get element by ID to run the script that I want. But of course, it's gonna be better if I actually know how to do this directly from this library instead of having to do it manually. I need to find a way to automate it. That's the problem. Because I don't want to, every time I create a graph, have to go there on the file and then change specify function to run a Python script. Barden-Sut is a credit tree-based gravity model. It is the fastest, default and recommended solver for non-hierarchical layouts. The more negative the gravity value is, the stronger the repulsion is. Network gravity. The gravity attractor to pull the entire network to the center. The rest length of the edges, the strong the edges springs are. A value ranging from 0 to 1 of how much the velocity from the previous physics simulation version carries over to the next iteration. JSON pickle.encode self max depth equals max depth. So here apparently it has a function to serialize. Maybe I can use this at the end of the script. Call this function to JSON. There is no explanation though. But I assume what it does is puts the graph on a JSON file or something like that. Yeah, but even then, that's not exactly what I want because yeah, it has to do with the HTML file, not the object. Maybe if I go and manually change the class itself and add the function to the class that adds what I want to the file, to the HTML when it's creating the graph. That way, every time I click on the portion of the graph, it's gonna do whatever I want it to do. Or every time I press the keyword key arrows, it accesses the list. I think I'll change. Oh, this one is very similar to the other ones, but it's a diamond instead of a dot. But it took a lot longer to draw, so still think the other one's better. But I like this one as well. I think it's slightly better to visualize this one. The issue is when it gets to this part, I'm not gonna be able to read this obviously. So I have to find a way to use arrow keys to go and get the information on them. Init. Mm. Yeah, let me. Access. It still looks really cool though. There's stuff behind the thing. That's the problem. Yeah, so I think I'm gonna change the shape and leave it with the dot because it seems to be the fastest. And the other ones that have the label inside, they're just trash. And now I'm gonna build it the direct graph, directed, to see how if it's any difference. After I do that, then I'll change the source on the target. This was much faster than the other ones. Yeah, so title, main, ID. So the node is just the the object inside the list of nodes. And this makes it adds this description to the title, which I guess is not really useful. Probably the most useful is this value thing here. So I think I'm gonna erase this. Well, actually, I'm gonna print the value to see what it is. I'm gonna print the node. It's probably gonna be easier to see the value. The next iteration. Maybe I can print this thing too. I'll do it the other way around. Display or hide certain widgets to dynamically modify the network. Oh, this one is interesting. Let's see if I skipped anyone that might be interesting. I think I stopped here. Set edge smooth sets the smooth type attribute of the edges. Toggle hide edges on drag. Place hide edges. Place or hide edges while dragging the network. Place or hide edges. So it's pretty much the same function. Oh no, here's edges and here's nodes. So this might be useful as well. Yeah, this is taking a long time for some reason. Maybe I have to load it again. I have a feeling that it broke or something. I think it went down. I'm gonna try to open again. Or maybe because it's directed this time. So it takes more time. Displays are hard certain widgets shot dynamically modify the network. Usage G show buttons. Filter equal nodes edges physics. Art show options G show buttons. When such is true, the widgets will be shown. Default is such false. Only include widgets specified by filter. Valid options true. Give all widgets. List of node edges, layout, interaction, manipulation, physics, selection, whether. Type status bow, type filter bow, or list. Conf true, soft options configure enable. But it still doesn't show what it does exactly. To dynamically modify the network. Overrides the default options object passed to the Viz.js framework. Delegates to the math options.set routine. String representation of the JavaScript-like object should be used to override default options. Yeah, so I think I got a good sense from this. This is where the construction of the edges options takes place. So far, the edges movements can be switched through this object as well as the edge colors inheritance. Used for all user interaction with the network. And those mouse and touch events as well as the navigation buttons and the pop-ups. So this was what I was looking for. So I guess I can use this class interaction to do what I want to do. Can build a script with that. Or I can do it on the same script. It's probably gonna be better to do it on the same one. This is weird. It's taking a very. Seems like it's gonna take a very long time to do, to build. This for all default directions. Maybe I should try to build another one that is not direct and see if it's working. Because the only thing that I changed is this thing. I think we'll do this. And then I'm gonna modify here just for this time. Choose send as mouse and touch events. Hide edges on drag. Hide nodes on drag. Def get item. Self item self. Yeah, but this doesn't tell me how it works unnecessarily. Yeah, now it's loading a lot faster, so it has to be because of that directed equals true. For some reason it makes it whatever, I guess. Oh, directed equals true. That's Control Shift. Yeah. Yeah, so this is the length, and then main neighbors break. Yeah, I'm not sure if this is useful at all. I think I'm gonna try to comment this out as well eventually and see if it changes anything. And the value is 1 here. So I could probably use this node value to change the colors as well eventually. And this is still at 0%. Handles the HTML part of the canvas and generates an interactive option editor with filtering. Self-enabled filter none. If filter, self-filter. Def get item, self item. I need to remember what this dict is. And this get item. Remember there was a one of these files. Oh, it's this one. So yeah, but apparently it doesn't show here. Get members. No, this is inspect. I'm not sure if this is made up by them. Python, everything is an object. There are a lot of ordinary system call methods on these objects behind the scene, which is not visible through the program. Object under methods. GetItem is a magic method in Python, which when used in a class allows its instances to use the indexer operators. Say x is an instance of this class, then xi is roughly equivalent to type getItem xi. Method getItem self-key defines behavior for when an item is accessed. Using the notation self-key. This is also part of both the mutable and immutable container protocols. Function prints the type of the object pass as well as the object item. Like some other languages, Python basically lets you pass any object into the indexer. You'll be surprised that the test actually parses. To the Python interpreter, the expression is equivalent to this test.getItem. As you can see, parse is implicitly parsed as a tuple. So, I'm not sure if I really understand, but parses something, and here it's fucked for some reason. So for some reason it's not loading this. Maybe the graph is too big or something like that. And solve.dict. This article, look at the dict provided. Python uses a special built-in attribute dict to store objects' mutable attributes. Basically, dict is a dictionary with a key value pair of objects attributes. The dict attribute is not just limited to instances, but can also be available to the user-defined functions. Module classes unless. So I guess the best way to see what this does is to use it. But apparently returns a dictionary of key value pairs with the attributes. So I imagine it's going to return the nodes and the edges. Act as the camera that looks on the canvas. Does the animation, zooming, and focusing. So all these three functions seem really interesting. To what I want to do, but I don't understand them very well. Class edge options. So I guess in order to initiate this, you pass the network as the object into this class. And then you can call these methods. Neat self-random seed, non-broad layout, house, hierarchical. Set separations of this, the distance between the different levels. Set tree spacing, distance between different trees, independent networks. This is only for the initial layout. If you enable physics, the recursion model will denote the distance between the trees. Set edge minimization, method for reducing white space. Can be used alone or together with block shifting. Enabling block shifting will usually speed up the layout process. Each node will try to move along its free axis to reduce the total length of its edges. This is mainly for the initial layout. If you enable physics, the layout will be determined by the physics. This will greatly speed up the stabilization time. Hierarchical objects. Get in get item, soft dict item. We need enable false level separation, free spacing, block shifting, edge minimization. So this creates hierarchical structure. Represents the global options of the network. This object consists of individual sub-objects. The map to Vue.js modules of configure layout, interaction, physics edges. The JSON representation of this object is directly passed into the Vue.js framework. In the future, this can be expanded to completely mimic the structure Vue.js can expect. Let me see if there's anything else here that might be useful. This was the stuff that I already read, I think. Yeah, this was the one that I copied initially. So how the hell did they do this? Oh, so I can do show buttons here. Oh, I'm definitely gonna do that. copy paste the output from the generate options button in the above UI. Copy paste the output from the generate options button in the above UI into network.network set options to finalize your results from experimentation with the settings. Oh, this is really cool. So whatever you do here, you can copy paste this into this option. Set options. It's really small. It's kind of hard to read. What's going on here? Yeah, you do set options and then you pass in as a comment. Oh, I forgot to see actually. Yeah, it just uses directly into the object. It makes sense. Yeah, this one works and this one is still at 0. It's probably not gonna load. Or it's just taking a long time there. Not sure what's going on with that one. So there was another thing that I was going to test here. Oh yeah. Comment this stuff out. And run this. See if it changes anything. Then after I do that, I'm gonna change the sources and targets. Oh yeah, but now I'm making directed equals true. Which is probably gonna take a while. Or not gonna load at all. So if it doesn't load, I'm gonna have to do it without this directed.
Then that means that B is also a friend of A, means that is implicitly defined. So suppose another relation, that relation is the siblings relation. So if A is a sibling of B, then it also means that B is a sibling of A, means that is an bidirected relationship, you can say. So here we can say if D is connected to C, then C is also connected to D. No need to mention it explicitly. That relation is implicitly defined. Now let's go to the directed graph. So in directed graph, every edge is given a direction, means A is connected to B, means there is an edge from A to B, but this does not mean that there is an edge from B to A. If it is explicitly specified that there is an edge from B to A, then only there is an edge from B to A. But if it is not, then the edge is not present. So this relationship is like follower relationship on Twitter. Okay. So if A follows B, then it does not mean that B should also follow A. Okay. So this relationship is one directional, right? So see here, A is connected to D, but that does not mean that there is an edge
I'm
from D
also
to A.
gonna.
So if X comma Y, then it doesn't mean that Y comma X, right? And the third graph type is the mixed graph. So in the mixed graph, both edges are present, means there is a directed edge as well as there is an undirected edge. right? So the application of the mixed graph is the scheduling problem. So the job scheduling problem. In job scheduling problem, so suppose these are the jobs A, B, D, C and E. Then as there is no direction from A to B, that means jobs A and B are independent. Means there is no time constraint for jobs A and B, right?
And if I could make the directed work, it would be much better.
So welcome back to part 2 of this video series.
So I need to make toggle physics equals true. Show buttons. The toggle physics and then show buttons. I think I can do it on. I'm gonna erase this directed. I think I can do it here. Apparently it doesn't like that for some reason. Enable physics equals true. Maybe it's not necessary because I think the default is for it to have. I'm not gonna put filter, I'm just gonna do show buttons and see if it works. With a UI is used to dynamically alter some of the settings pertaining to your network. This could be useful for finding the most optimal parameters to your graphs, physics, and layout function. Yeah, so I'm gonna run it like this. Oh no, no, no. Fuck. I have another one already opening up there. Well, hopefully it doesn't fuck this one up. I think I have to close this file as well. Yeah, this one is gonna go much faster. So I think I'm gonna have to think about different ways to manipulate the connections. Or maybe I can also play around with this classification stuff and see what it does. Yeah, I think I'm gonna do that before I think about going the route of trying to manipulate the HTML directly from another script, because that's probably gonna be a lot harder. Yeah, I want to be able to add things that are not necessarily from this library into the same HTML object. The other option is to try to create a new class inside of the file that has this. Or maybe it doesn't need to be inside, just a class that takes the object and does stuff with the object. And then I just have to understand how the HTML is being built. Because just by reading this, I still don't understand it. I'm gonna wait for this to load and then I'm probably gonna rest or do this off stream. And the other one is loading apparently as well. It's at 30%. So hopefully the directed works now. I think it's just because it takes longer maybe than the other one to load. But I think it's gonna work. If it does work, then the directed is obviously gonna be better because it's probably gonna show the direction of the arrows, which is the representation of the execution path. Yeah, but maybe the way that I'm doing this is also wrong because I shouldn't be connecting function name with function file name. I think I need to create different connections, different types of nodes in this iteration here. I can create a list with the columns. Yeah, but the order only matters if it's a directed graph. So Not really sure. I think the easiest way to. No, but the thing is, I have to understand it. Yeah, so the title thing doesn't change anything, I guess. So I think I can remove that line. Doesn't make any difference. And it didn't show the buttons as well. So I'm probably doing it the wrong way. Maybe I should be calling this at the end there. Before this. And now it's giving me a warning. Too many blank lines. The other one is still at 70%. 75 now. So I think here I'm just gonna change this to function name. Function file name. Then I'm gonna make this the source. Color file name, the thing. Yeah, the other graph is done, and apparently it worked. It's very different. Not very different, slightly different. So function file name is gonna be the source. And color file name, the rest is the same. Function file name, color file. And I want to see how different this is, and I think I can erase this line here. Yeah, this is correct. So let me first see this. Apparently, for some reason, oh, now it worked. Just took a while there. Yeah, but it's a lot heavier. Yeah, so here is displaying the arrows. So it's probably better, but a lot heavier. True. See, that's why it was taking a lot more time. So I think on the final graph, it's better to do the directed, but just to test things, it's better to do the other one. I guess is the physics of the thing. It is making it really heavy. You can even play around with the thing. So maybe the arrows are unnecessary. I just need to figure out. The main thing is to figure out how to create a script or something that allows me to navigate using the arrow keys and to highlight specific things based on the arrow keys. I think I can do that with the set options stuff, probably. So I think that's the path to go. To figure out how to display the buttons, then to set the options. Then when setting the options, maybe I can write a function that allows me to travel through this with the arrow keys. The thing is, I'm not sure if there is a list or something like that on the HTML. I think there is from the brief look I gave, but this is very heavy. So animations and colors. Now let me run this because I changed the source and the target. I think I'm gonna add a comment here just so I don't forget. Make direct goes through wait graph with arrow representation. Presentation. Yeah, so here it is. Huh. So this is different. That's weird. What did I change here? Oh, I changed this function file name to color file name. So completely different graph. And here you can see that is giving these loops. So I guess every time there is a circular call, let's say, these loops show up. So I also have to play around with the set trace part to see if I can extract more information other than just the functions. And this is not showing as well the options. So this show buttons is not working. So what else? What else gonna do? Yeah, the problem there is no way to connect. Trying to think about how can I connect more than two columns in a sequence, but the edges are only gonna connect two at a time. So I can't think about a way to change each time. Maybe I can make another edge. Below this one from destination to another thing that I put here. I think I'm gonna try that. This function name, function file name, color file name. Wonder if I can change the text as well. Mm. So let me try this. Add node. Destination. True. I'm gonna make the source the function name. Destination file name, color file name is gonna be echo. Then I'm gonna make this. And then here I'm gonna add another edge from destination. Destination true. Let's see what this does. So hopefully what I'm imagining it will do is gonna connect the function name with the file name, and then the file name with the color file name. Maybe it should be the other way around actually. Should be color file name, true function file name. function. I'll try like this first, then I'll try the other way. And here I have to see the module code again for the network to see the options thing. Where was this thing? Show buttons. Displays or hides certain widgets should dynamically modify the network. Usage g.show buttons. So maybe I need to put the filters. But it should be calling, well, yeah, if filter is equal to none, it's probably not gonna show anything. Because by default is none, and it doesn't show anything. So maybe the filters are necessary. A parameter status. When such true, the widgets will be shown. Default is such false. Only includes widgets specified by filter. Valid options true give all widgets. So maybe I should put true. God damn. The graph is done, the other one. And apparently it worked. But it's constantly moving. So I guess I will have to change the repulsion and the physics, probably. Layout, interaction, manipulation, physics, type bow, type filter bow, or list. Self options, configure. Toggle physics, self status. Toggle physics, memory status when false. Nodes are not part of the physics simulation. They will not move except for manual dragging. Default is set to true. So maybe I'll set this to false eventually. But first, I'm gonna try to play around with the show buttons thing. It seems more useful. Set options. Overrides the default options object passed to the Vue.js framework. Delegates to the math options set routine. Parameter options. The string representation of the JavaScript-like object should be used to override default options. Yeah, so this is probably the way that I'm gonna do it. I can just do the set options and then I have to figure out a way to do whatever I want. There. So this is the result of the other one. And it's constantly moving because of the repulsion stuff, probably. Which is obviously not ideal. It's interesting that it works though. Yeah, so I think what this is doing is creating the same one as before, where I have the files with the function names of each one. But in addition to that is connecting this to to the color files. I think I'm gonna run it again. And now there's no outside files here as well. In the other one there was some hanging ones outside. If this doesn't work, I'm gonna try to set status equals true and try again. Yeah, this one has these verbose functions here. So the other one, I imagine that they're being connected somehow with the color file. Oh, these ones are probably the color files. No, can't be that because they are function file names. Yeah, so these function file names are not connected to anything directly, but they are connected to the color file names. And that's the difference. I guess these line numbers are pretty useless, actually. Or they might be useful. Yeah, they're probably not very useful because I'm only gonna search for the files and not necessarily the line number that the function is being called, but I guess I'll leave it there. Because I might change my mind once I actually start using this to study. Yeah, it's still not showing the physics thing. Maybe it's because, well, it's not because of the size, otherwise it was probably gonna show a bar here. Yeah, so see, find cookie detect, which is lost here, and here is attached to this file, which is attached to the other ones, tokenized by. Tokenized by is not attached to any other thing, but it is attached to the color name, to the color function, the colors file name. Maybe if I try the other way around. So I'm gonna try two more things. I'm gonna try to set it to true status. The widgets will be shown, default such false. So unexpected argument. Unexpected argument. And that sucks. How can I use this? I created the object here, then I'm accessing the function. Which is this network. These are high. This center just dynamically modify the network. Usage G show filter. Show all options. Yeah, but I tried without anything and didn't work. Maybe if I do it on the same line, but it shouldn't matter. Only include widgets specify the filter. Valid the options true gives all widgets. Maybe if I try filter true. Tab status bool, board list. Display of a graph is achieved by a single method call on network.network show after the underlying network is constructed. Directive visualization is presented as a static digital alpha. So maybe I need to do this not enable physics true. Maybe if I just pass through here as well. Yeah, but then start screaming. Unexpected argument. So I guess it only takes one argument. Then that. Go. Yeah, it's not showing the. Oh, it is showing. I'm so dumb. It's on the bottom here. It's because in the example it's showing on the side, but I guess it's because of the size of the graph. It just stays on the bottom. So maybe for this I should create a smaller graph. Oh, I can change the font here. Interesting. I can change the size as well. Yeah, much better. Let me see if it changes. Yeah, it definitely changed things because yeah, it definitely changes. Cool. Now let me toggle the physics off. It's still changing. It's still moving. Arrow strike through. Oh, now it stopped. Interesting. So now it only moves when I change. But there is still this pull of the edges. Uh, what else I was gonna see here? Arrow strike through. Didn't change anything. I think of all the graphs that I made, this layout is probably the best one because it contains the most information. And I think it's correct the way that it's built. It has a connection from the function name to the file name, and then from the file name to the colors file name, which I think is the correct way to go about building this. But it's obviously ridiculously hard to read. Yeah, I don't understand what the arrow strike through changes. Let's see if I put hierarchical, what's gonna happen. Yes, I can't do it apparently. Or maybe I can, but it's just it's probably gonna take a while. Not sure exactly what it is, so I don't need to toggle this stuff. So I think this part is correct. Function to the file name to the colors file name. I think I'm gonna do it the other way around just to see. Reversed. Oh, this one stays the same. If I go from the color name to the function name to the file name. Color function file. Yeah, it doesn't make sense to go from the color to the function name. So I think the function file name should be on the middle because it's the bridge. It's the bridge of the connection. So let me run this. And this one is still broken. Oh no, there we go. Also I can change here, but for some reason this crow, yeah, it's because I changed the hierarchical stuff there. After this is done, I'm gonna change this. Revert these changes that I made. So now I think the path is clearly to play around with the buttons options, then play around with the set options to see if I can create the attributes that I want, if I can create the manipulation that I want. And I can just use the index of the nodes instead of the set options to figure out the display and the animations. I think I can set I think I can make the animation based on color, like changing the color in a loop. Change the color attribute in a loop. Every time I press a key, for example. If a player press space, then it changes the color in a loop to show the animation of the execution. And then if I press another button, then it stops. I think that's the best way to go about it. So here is pretty similar to the other one. Don't see, but it's definitely different. But it's hard to know which one's better out of them. Or maybe this one was the, no, this is the new one. Yeah, simple reverse. I think the first one is better. It makes more sense to me, I guess. But I'm not 100% sure. I also think I'm gonna make it smaller next time. Just see if I can fit in. Maybe I can keep the height the same, but yeah, so I can do it like this instead. I'll put 50-50 here. Yeah, so the next step is gonna be to figure out this animation. The animation and the set options stuff. Once I figure that out, I'm gonna see if I can change the script to see if I can change the, so if I can change this script here to see if I can get more information other than function names and create a different data frame. Then once I have that, then I can test it, can up the script that I wanted to study, and I can test. I also need to integrate the graph with the opening each file based on the key press as well. So I'm gonna have to see how to make that happen. Because I want uh, to have the option to open the files and the scripts as I walk through the graph. I'm probably gonna do this another time. I'm already tired. Oh, I mean, I completely forgot about the weight as well. But I think it's not necessary because the graphs already contain the information. Oh, so this is still loading. I'm gonna wait for this and then I'm gonna be done for today. And continue this another time. Oh, it's done. I wanted to see the options. So there, generate options. So it's pretty much a function, a variable that is equal to a function that has these properties here. And I assume these ones are the properties used on the CSS. I'll have to study more about that to see how it changes. But I'm pretty sure I'm gonna do something with the color. Yeah, I'll do this another time. I'm really tired. I'm gonna take a break. And I'll be back another time to continue this. So see ya.